thank the organizer for inviting me to this wonderful meeting in Singapore. So today I'm going to talk about something completely different from my last talk, and actually it's not so much connected to the theme of the conference. It's very much algebraic geometry, but I think it's something that is entirely new and exciting, and it's very simple. So I would like to share with you so that I attract more people to work on these kind of problems. It has been very instrumental to prove fundamental lemma, to study the geometry of Hitchin fibration. So Hitchin fibration is moduli space of Higgs bundles over algebraic curve, right? And so Higgs bundle, if I exist in any dimensional, and it's a very important, but a very fundamental theorem of Simpson, saying that there is a moduli space of local systems, of connections, and of Higgs bundles, which is more technical and conditioned, are topologically the same spaces. And in the case of curve, it's not completely well understood, but because this duality, this isomorphic space, is somehow very related to Langland in some way. It's not, for example, in you talk yesterday when you count from local systems and related Hitchin number Hitchins. So there's a lot of coincidence that's been they've been used but I don't think that is somehow a complete through understanding of it. But here I want to move on higher dimension to study the moduli space of Higgs bundle in higher dimension case. Although there is no more any relation with automorphic forms. Automorphic form is very much kind of one-dimensional theory on higher dimensions. And I just try to see what I can do. So it's some very simple basic things. And, but before to do that, let me maybe spend like 20 minutes so to recap the formalism in the one-dimensional case and to see how can generalize on this in higher dimension case. Okay. So by the way, this is a joint work with Hitchin, who was still in Chicago, but he's going to join Minnesota next year. So let me start with the case of curve. So X is a smooth projective curve over some field K. So it doesn't, do algebraic geometry, it just didn't specify K. And so Higgs bundles of rank n over X is a pair E and theta, where E is a vector bundle of rank n over X, and theta is a map from E to E twisted by the one form of an X. So this is OX. Linear map. So it looked very much, form looked very much like a connection. So the connection is not OX linear, but satisfies some kind of Leibniz rules. So when we study harmonic analysis, we somehow replace omega 1 by any line bundles. But for geometry, it's very important to be omega 1. So let's keep omega 1 here. Okay. What did I say? So we have this space of M of E theta. So the moduli space of all these pairs is this Hitchin moduli space. Of Higgs bundles of rank n's. So again, in geometry, maybe it prefer to study instead of stack, moduli stack. So to study moduli space of stable Higgs boson, and that is the one that really connected to the space of representation. But here you just look at the Stucky point of view, which slightly somehow it's more abstract, but it's slightly more it's more elementary. So now we have this Hitchin map. It's a very important map, which is not very elementary, but it's quite. Is the map from this space of M. So this space of H to A. So A is a higher dimension, a fine space, which is a direct sum of space of symmetric differentials. So here's the one dimension, it's just tensor power of omega x, right? And the map in this case is completely obvious. Is space map E theta to A1, A to AN, where AI is the trace of wedge I. Theta is going to go from wedge I of E, go to wedge I of E, twist by symmetric of omega x. So the way, I mean, exterior and symmetric tensor setup that you get this, in the trace of it you get this symmetric differential form of, and this is the map. And and if you when you, on the trace formula side, you can say M is some kind of whole trace formula, and each Hitchin fibers a space of conjugacy class or stable conjugacy oblongations. And so this map is very much kind of geometrization of the geometry side of trace formula. But here we try to more interested in the geometric feature of this. And the main features of this map is it is in abelian fibration. Is it mine? Oh, sorry. Sorry. Not expecting this. These are abelian fibration, which means that for A in a generic point, then the fiber H minus 1 of A is essentially abelian varieties. Is abelian varieties up to connected component and some in inertia. So some group that act trivially because they are in static business. And somehow it's very, this is very important, and then, we usually want to prove that somehow these kind of structures, very smooth structures, determine on the singular fiber in some specific way. Okay, so now, but in this talk, I really want to understand this phenomenon of abelian fibration in higher dimension, not go into any singular fibers. So how to describe the fibers of this is, the way Hitchin understood it is very elementary, very elegant. It's called spectron curve. So how you can prove this in the curve case? That's why Hitchin defined what's called the spectron curve for every A in A. For any coefficient of this characteristic polynomial, you can define a curve that is the spectral equation. Give rise to YA is a curve inside the total space, so the cotangent space of X, and which map on X is a n-fold covering. Defined by the equation Tn minus A1 Tn minus 1 plus n An. So you have X, let me draw X as kind of line, and then the cotangent is some kind of surface fibers over X, and every fibers are just a fine line. And this is, you have the spectrum curve, something like this, and this is YA. And this is kind of a three-point carving over X, and it unramified almost everywhere. And T is the coordinate, the vertical coordinate. And it's set up the way that it actually makes sense. I don't want to go into this, but it's set up the way the equation makes sense. And he observed that if Y, no, let me check. It's just by the Cayley-Hamilton theorem. You know that the MA, you can identify MA or the fibers of H over A can be identified with the space of F, which has OYA modules, right? So you use theta to define E as module over the cotangent. And the Cayley-Hamilton theorem says that the module is supported on the spectrum curve by a module such that E, which is PA star of F, is a vector bundle on the Planck end. Right? So we start with E, and because of the theta, E become an F. So that E equals PA star of F. Right? And we should want that E should be vector bundle. And the condition vector bundle for curve is very easy. It's just something that is torsion free. And so this implies that, for example, if YA is smooth, we just say that MA is invertible OYA module F. So this condition, the kind of view condition that the PA star is vector bundle, can be translated into a more natural for the curve. The spectrum curve is just invertible shift. If you know that this spectrum curve is smooth, right? So in general, for every A, you can define PA to be the pK varieties. So in this case, it's essential abelian varieties up to the connected components. So this is Jacobian of YA times Z for the connected component and divided by GM in inertia group as actively. So in general, let PA to be peak of YA. So they are invertible shift on YA. Then you know that it acts on MA. Right? So this is the for any spectrum curve. So this is some. So you see the curve, the fibers themselves are not the abelian variety, but they're acted on by some abelian variety. So all these features it should be generalized on every groups. Then I set out to do it. So the point is that for every group, for general, he said no spectrum cover for general group. For classical group, you can set up some kind of spectrum cover with involutions. But this kind of theory is kind of case by case. So in general, there is notion that by Donaghy, introduction of Donaghy, of Cameron covers, which fit very well with Lie theory. So let me describe these constructions. So now for simplicity, I just assume G to be a reductive group over C. So it can be over any field with some kind of reasonable assumption, like a characteristic does not divide by the order of the Y group or something like this. And we have Lie to be Lie of G, the algebra acted on by G. Then we know this theorem of Chauvelet theorem. We know that the K of the ring of G invariant functions on the algebras is isomorphic to the ring of a W invariant function on the Cartan's algebras, right? And this is also is a polynomial algebras. So these polynomial algebras, so that these functions are not quite canonical, but they can be, but the degree are canonical. So that A1, AN are homogeneous G invariant polynomial of degree d1 dn. And it is the exponent plus 1 or minus 1, they could be canonicals. So, so let's rephrase this into some kind of abstract language that really allow us to, to put on this construction into kind of the very transparent footing. So this is when you have the action of a group on a space. So let me draw it here. Then have this notion that you have just mode out. This is a quotient is stuck. Quotient, stuck quotient. So we can perform some kind of quotient stuck sense of way. But the fact that you can describe the space invariant function and that have a natural map into G. So this is an algebraic stack, and now the quotient is a space. Right? So space that supports the stack somehow. So this is an unified space. Right? This is the spec of KG. G. And let me call this C. Chevrolet. And okay, and then and here you have action of GM act by homothéty, and here the GM action act by the exponent. That means T act on A1, AN might be T of D1, A1, T of DN, AN, right? So that make this map compatibles. So with this, we have a transparent construction of this Hitchin map. You have a Hitchin map is, if you just unravel on the definition, Hitchin map is a map from X to this quotient basically. G mod G times GM. So there's some GM, and to put it to the truth by the canonical bundles. So this is E theta, right? So this is kind of very abstract. The quotient is abstract. This is by definition, there's no theorem here, right? It's just this stuff is defined, this map, it's just the data that I wrote before. And of course, this is over the BG times BGM. So classifying space of G and GM. So this is over, of course, it's over E. So the BG corresponds to G bundle E over X. And the GM, this is just omega of X. Right? It corresponds GM bundle given by this Lie bundle, the canonical bundles. Now, because of this, you can compose this into C mod GM, right? And this is of the A. So this map is just a space of symmetric differentials. And the degree is just given by D1, D2, Dn. So that is very, very, this is the, well, I mean, it takes a while to integrate this in your mind, but when you do it, it becomes very, you don't need to think much. It just comes to have to draw a diagram. And so you also understand that so this, that this is T mod W, by the Chevalier theorem. So when you have this X, you have X mapped to C mod GM, then you have T mod GM, T mod W, sorry, T mod GM. So this is, and this is W covering the T mod C. So somehow you just can forget this GM. It just doesn't play very minor roles. It's just to be remembered. It's twisted somewhere by the canonical bundles. And this is the Cameron covering. This is the Cameron covering of Ludonagi. So this Cameron covering allows it basically to reconstruct this. I mean, it's more elaborate, but you can generalize the spectrum curve in some kind of uniform ways. Okay, just one last word in the case of curve is in order to, I mean, that is a very basic structure that you can want to construct in for every group. And in order to construct PA, the essential ingredient is upon the regular centralizer. So this is also very elementary constructions. So you have G. This is the algebra G. This is mapped to C. The space of characteristic polynomial, the T mod W. And over G, we have I, which is the centralizers. Right? If X in G, I of X would be G in G, so that G at G of X is X. Right? So this is some complicated group scheme over G. But inside G, we have a G rec. It's much nicer where the centralizer is dimension, minimum dimension, right? Inside this, and you have IREC, the restriction. So IREC is smooth abelian group scheme, right? So there's the largest open subset where the centralizers have the minimum dimensions, and which is abelian, right? And what is quite a simple but very important observation is actually, so let me call this guy, this is chi rec. This thing descend. So there's no way to descend I, but the I rec descend to the base. So here the claim is that there exists so there is this unique smooth abelian group scheme J over C with a G equivariant. So the fibers of G rec are homogeneous space. I mean, the regular matrices are conjugate, right? Once they have fixed characteristic polynomials, are variant chi rec star of J to I rec, right? So I rec descent. So there's a unique smooth group scheme. You can pull it back, and moreover, this extend to a homomorphism, to a unique homomorphisms, chi star of J to I. So that's it. So what I mean by this is something very elementary. You pick a matrix, right? You look at these centralizers, these some groups. But I want to produce a group that doesn't depend on the matrix, but only the characteristic polynomials. So how do I do it? So instead of the matrix itself, I choose some regular matrix which have the same characteristic polynomial. And I pick a centralizer. And I prove that that tensor vector doesn't depend on the choice of my regular metric. It's canonical. And moreover, that group just actually map canonical to the centralizer. The map can be trivial, maybe just go to 1, but it is canonical. Okay, then one have this. You have the you can have then every A from X to C. You can put back GA to be A star of J, and you define PA to be the space of JA toxers over X. So this is a little bit kind of jump abstract things, but this is just I want to just show that some kind of very canonical construction of everything. And then with this, PA play the role in this Picard stack. And when you don't have a spectrum curve, you have to go through this kind of group scheme construction. You have this PA, and PA acts as this canonical action comes from these homomorphisms. This homomorphism gives the action the PA over MA. And when the spectrum curve, when the Cameron curve is smooth, then this action is simply transitive. Right? And PA is actually a billion varieties. So when so PA act on MA for every A, but when the spectrum curve is smooth, then this action is simply transitive, and PAS has a billion varieties up to pi naught and inertia. And somehow, in general, this pi naught is actually that's possible in endoscopy. How we can construct some kind of geometric endoscopy theory by studying this pi naught. Another thing is very interesting. You see that basically there is a duality. The inertia and pi naught is some kind of dualities. In the sense, when you go from G to G dual, the pi naught becomes the inertia comes to the pi naught. Something like this is very important when you study dualities. Okay, that's about what I want to say about abstract structures of the Hitchin moduli space in the case of curve. So now I'm going to set out to try to do something for higher dimension case. Of course, now it's very low level, it's not going very far, but I think there's some kind of structure that emerged and that deserves to be studied. Okay, so if you want very much to set up all these structures in the higher dimension case, so let me go to what the Hitchin. So now X is some smooth, proper algebraic varieties. So we are going to soon some point to go to dimension 2. After dimension 2, do not lose very much because we're a fundamental group, and the cutting by hyperplane doesn't change the pi naught. So the pi naught, the moduli space of a fundamental group for higher dimensional varieties can be reduced to the curved surface, and the same is true for Higgs bundle. So the curved surface is a crucial case. But anyway, you can start with any dimensions, and then Higgs bundles. This is Higgs bundles. Is a pair of E theta, where E is a rank n vector bundle over X, and theta again is just a map from E to E tensor omega 1 of X. But with one condition that makes the whole thing more difficult. That is very integrable. I mean, when the theta wedge theta equal to 0. So that is the condition that makes the study difficult. So this is integrability conditions. So in other words, you can, instead of this, you can look at theta as a map from E tensor the dual of this, which is a tangent bundle, mapped to E, right? And this is OX linear. Then we have this action of the vector fins on the vector bundles, action, linear action. So what does it mean? That if you trivialize, so locally, you write E as OX to the N, and TX is just OX to the D. The D dimension of varieties, so they are sum over I from 1 to D of OX fraction of XI. So you choose some coordinate that you can get this, right? And so this map is just decide how this fraction XI act on this. Right? This map that the theta of fraction XI would be theta I, and theta I is just endomorphism of E. So theta I is endomorphisms of OXN, and these conditions just mean that this map is commute. So you want that theta I map theta j equal to 0, right? So that's it. So we just want the vector bundles with basically D commuting matrices endomorphism, but twisted by the omega. So this is a little bit, to put some stocky thing to exorcise this omega x. But now you want to see what is this kind of target scheme. What is the how to redo this construction in higher dimension case. And obviously you have the kind of target stack. Would be so now let G some kind of reductive groups, not necessarily G and Len, and then you have the code C, kind of commuting varieties, commutatorium, whatever, and you have look at the map, the stack of on maps from thetas from a vector space. Of dimension D, right? So that is a kind of model for a tangent space, just take vector space dimension D, that map to the Lie algebras. So it's just a linear map from a vector space dimension D. It can be 0, right? Just don't need to be injective. It's just some map, such that for you have that theta of V, theta V prime should be 0. So you want the space that it just commuting element. So for example, if G is to contribute G and Len, and D is depend on D, and D is 2, then if we rigidify V to be the A2, then C become just theta 1, theta 2 inside G and Len, just commuting matrices. Right? Then you divide by Gn2, right? If you were to divide by Gn2, because this is some kind of basis of V, but you can choose another basis in commuting Gn2. So anyway, so you want to divide by G. G act by, so G act by transaction here. Somehow and G and D act on V by transfer. So we have now the Hitchin fins. If we follow this kind of logic, is have this, it's just a map from X, from E theta to this commuting scheme, commuting stack. So C. So C is divided by G, and also have the action of G and Len. Okay, and this is this map to V, and this is map to B G and D time BG. And on the BG and D, we get the omega of x, right? And on BG, you have E. Right? So this is the map. So giving a Higgs boson, you can describe Higgs boson as space of map from the surface to some kind of target stack. And this kind of target stack is just space of some commuting matrices and divide by the whatever natural action they have. They have a natural action on G and some kind of base changing action on vector space. So G and D times G. And after twisting, you want that the G action be give rise to the G boson we start with, and the G and D action give rise to the cotangent boson. So that is it. Okay, so now we want to now we come to the. So this is really studied in the important paper of Simpson, and Simpson defined a kind of Hitchin map. Only in case of G equal to G and length. So how he define it? He define Hx is mx to ax. So it's very similar to one-dimensional case. This is direct sum of I from 1 to n h0 of x, si of omega x. But now it's much more complicated because in one dimension this is a Lie boson. Then si also Lie boson. It's just tensor. But here Ox is rank D vector boson. The sim I of that kind of complicated stuff. And he divided this E theta mapping to A1, AN, where AI is the trace of theta I of E mapped to E tensor Si omega x. So it looks slightly different than the one case, but it's the same. It's just how to choose another base of symmetric polynomials, another. So this is not a big deal, but it's easier to write in this way in higher dimension case. So now the problem is how to describe this Simpson-Hitchin map. So it is an abelian fibration. Is this map abelian fibration? So that the answer is actually no, but you can so the Parkson answer you have this have a factorization of this map. Let me call this Bx. A Bx and something in between Ax. So you can define some kind of closed subscheme of Bx. So the image is very small. From Ax is closed embedding. And this is an abelian fibration. So for GLN, you can for surface, you can prove that you can define a subscheme of Bx, closed subscheme, and then it's factorized. This will be abelian fibration called closed subscheme. But what we think is very complicated. I have no idea how. I mean, I can describe the equation, but what the geometry of this is very difficult to understand. So the geometry of Ax seems to be connected to intrinsically into algebraic variety of higher dimensional varieties, like classification of surfaces, stuff like this. So that is why I think it's very important. I mean, it's very quite exciting how to connect the Hitchin correspondence between fundamental and group, and to have the geometry of Hitchin map, and this kind of bizarre looking subscheme and how it is very different from one variety to another, and we didn't understand it. But at least, so let me continue how how can define Ax and how can prove this map actually be abelian fibration. So for that, you have to come back to this, to understand. Remember, in the case of curve, you have this map from G mod G to G mod G, right? So this is the basic kind of the mother structure that we give rise to the Hitchin fibration. And now we have this more complicated stack. We have bunches of commuting matrices, and we want to define some kind of the space supporting the stack, right? So here there's some kind of space, but this is enormous. So we have to get some kind of smaller space supporting the stack. Now let's do it. So there can kind of very elementary called spectrum data. So spectrum data is something, something more refined than this just taking symmetric power. So what I mean by this is if you have V, so now G equal to G n length, right? And so let E to be n-dimensional vector space. So now you have one theta d, some endomorphism of V, commuting endomorphism of V, so the theta I, theta j equal to 0. Then you can endow E with a sort of a module of a polynomial algebras. Right? You can this E become a K of x1, xd modules of of finite length, of length n, where xi act as a theta I, right? And the condition that is commuting, that means you have to have a module of polynomial algebras. And so with that, you can define spectrum data, the most simple manner as possible. You write E as decomposed direct sum of E alpha. Alpha is the point over the n-dimensional space. So alpha is in, let K be algebraic close to simplify, so K to the n, right? So you just finite length module, you just have some kind of finite support. You just split over the finite support. So E alpha is supported by the point alpha inside K to the n, right? So K algebraic close to avoid rationality problems, right? So you can, a module, finite module can be direct sum of simple modules. And so it just now the map is just mapped into this into the 0 cycles. So we no longer care about E alpha, just remember the point and the length. Right? We have sum of alpha of length of E alpha time alpha. Right? So we have this is called spectrum data. I mean, the most naive thing is in the vector space. Just remember the eigenvalues. Eigenvalue is the point on her, and the multiplicities. That's it. You forget about everything else. And this thing is in Chow. In the Chow scheme here is very Chow is very simple. It's A, D, N. So n symmetric power of AD. So it's not symmetric powers as vector space. Symmetric power as algebraic varieties. So this is AD and divided by Sn, right? So this is, there's so much symmetric powers, it'll be confusing, but here it is symmetric power as a space and not as a vector space. Okay, and then that's it. And what happened is this construction works over any rings. And surprisingly, it doesn't seem to be trivial to do it for other reductive group. I mean, I haven't managed to do it yet. It should work, but it should something like this. But over fin is easy, do it over any arbitrary ring is kind of tricky. And here generally it works. It's not trivial. I mean, have to go back quite deep into EGA4 to find the right construction for this. But anyway, it works. They have a map. Yes. No, G, I replace G by Gn len, and the torsion, the G is a vector space at dimension n. Yeah. So in general, you have I mean, so here what I mean in geometrically, you have so let's say C to be commuting varieties, right? Let's change the notation a little bit. This is x1, theta 1, theta n, theta d inside G, so you got theta E, theta G equal to 0. Let's forget about the stocky stuff, just D commuting matrices. And so what I mean, so the problem here is the following things. You have the you have map, have this GIT thing, the G invariant function on C, and you know nothing about its reducedness, not known to be reduced. But if you take reduce, this becomes T to the D divided by diagonal from the W. Only the reduced part. It should be reduced, but nobody can prove it. And so there's a natural induction from TD mod W to this C divided by G. But here somehow we have a map in the opposite direction. Some kind of linear algebraic action in the opposite direction. And this is not as strong as reducedness of this, but it's quite strong. I mean, somehow what is enough to on geometric construction to produce some kind of map. You see, even in the one-dimensional case, it seems it's kind of obvious, but the fact that A1, A2, AN on the symmetric polynomials on the carton can be extended as a function on Lie algebras, it's not obvious. I mean, it's something that should happen, right? But it's not. There's no abstract results for it to be solved. So it's kind of the same problem. It's much more severe here. But anyway, there is it's just seen as some interesting problem here, in even for group theoretical problem. So. Okay, so with this we actually have the map. You have a map from the Hitchin map from MX to AX, where AX is actually Chow n, some kind of relative Chow n from the cotangent. So that means for every fibers, you pick out some zero-dimensional cycles, and you want them to vary algebraically in X. And that this construction, every time you have Higgs boson, you have a relative Chow point, and that is AX. It looks complicated, but it's what seems to be natural comfort. And then now we have the point you have map from AX to BX is closed, emergent, right? And so this map is going to see that it's kind of built in fibration. It looks very much like one-dimensional case, and this is closed embedding. But you don't know what the dimension of AX is. It's kind of a difficult question. So why this is closed emergent? This is also very kind of funny invariant theory. So this is, I have to offer two lemma. When I do it, I thought it's completely new, but then doing friend told me that both, almost, was already in Vi book on invariant theory. So it doesn't matter. So the first one is, I think the first one is the first lemma in Vi book is this is in Vi, that you have, V is a vector space, and the Chow and V map to V times S2V times SNV. Right? Chow n is just collection of n vectors, n orders. So if you have V1, V2, Vn, so n orders collection of vectors, you can map to V1 plus Vn, V1, V2, etc. Right? And that gives this map, and this map is a closed embedding. Right. So in case V1 dimensional, this is kind of usual things. You have n numbers and check this kind of characteristic polynomial. This is isomorphism. Let's say that the symmetric, this is the ring of symmetric polynomials are generated as a polynomial ring given by generated by this element of symmetric polynomials. So this is the same is true in higher dimensions. It's no longer an isomorphism, but it's a closed embedding. Right. So, well, you can write out the proof. It's pretty quite interesting. So that this lemma proves that this is actually a closed embedding. So when Simpson proved this, so H have to give right to this, but this is way too big. It only had to factorize through this much smaller thing, the Chow n. Right? But now for arbitrary surface X, to specify what is this subscheme is kind of difficult thing. It's not easy. Anyway, then the second lemma, also kind of cute, is you can look at this map chi n from V times Chow n of V to the symmetric power. So this is a symmetric power as the varieties, and the symmetric power as vector space, right? And you map V and the collection of V1, Vn vectors, and you map to the product. V minus V1 times V minus Vn. So that you get the symmetric tensor. Right? You have a map, and you define that Cayley for Cayley-Hamilton. So Cayley of V is the chi minus 1 of 0. Just vanishing by this kind of Cayley-Hamilton polynomials. And the claim is that this map is you have this Cayley of V, maybe n of V, mapped to Chow n of V. So we project this thing onto V, this factor. Right? It's very much in the K one-dimensional K, just to generalize in V in higher dimensions. And this is a finite map. Finite, but not flat. Map. And this is a tan over the point where all the vectors are different. Okay. So I don't have time to explain, but it's very, you can describe exactly what it is. What is the fibers of this Cayley map, but the dimension kind of jumps, the rank kind of jumps. When V is one dimensional, this map is a very nice finite flat map that gives rise to the spectrum cover. But here it's not flat. So now when you have A when you have a map from X, so A in A of X, A to this child, relative child and for tangents X over X. So this is A, right? That's how the spectrum data given by the section of the relative child scheme. And then you have this Kelly N. So this is finite. So again, like in the one-dimensional case, you just form the XA. So this is finite, but not flat. So in order to make things nice, you really need to do the Cohen-Macaulay. So this is when X is a surface. So thus now we have to restrict ourselves to the kind of surface case. Then there's some kind of very nice kind of resolution. It's called the Cohen-Macaulayfication. Macaulay spectrum surface. Right. So each of the one that is kind of canonic, that make this map is finite and flat. So this is coincide with XA almost everywhere. At some point you have to modify it to become finite and flat. And this is possible in the case of surface case. Right. And then you can prove that you have PA to be the pK variety of XA Cohen-Macaulay, and then PA act on MA in one-dimensional case. And moreover, if XACM is normal, you don't need smooth, just it should be normal. And then PA is, and then this action is simply transitive. And PA is the Nabelian varieties, also up to the connected component and inertia. And so you can have a very, very good theory of spectrum surface in the case of surface by going one step further. You just not to check the spectrum cover, but do a kind of slight modification of it, the Cohen-Macaulayfication of it. And then the pK variety of that stuff is going to be to describe the Hitchin fibers. Yeah, but well, it worked very well in abstract, but given every surface to do calculation is kind of absolutely horrendous. You can do it in some simple surface like a abelian surface or fiber surface, but just given some kind of general type surface, I don't know how to do it. Yeah. And also, I think this, there's a lot of questions. What I really like to how to have a way to have another look on the very classical theory of algebraic surface by studying this kind of geometry of Higgs bundles. Okay, stop here. Sorry? Yes. Well, mere implementation theory in invariant theory is very important. Yeah. You don't understand it yet. I mean, all this story about the commuting varieties is still studied kind of, yeah. But it's kind of surprisingly knowledge is very poor. You don't even know the thing is reduced. It seems to be very hard. Even n to 2, I remember. We know what is the reduced varieties is due to some Joseph, Anthony Joseph has result on this, and but you don't know if it is reduced or not. Just for G and N, because I'm kind of stuck on this map. I don't know how to define the spectrum data map for other group G. I don't know. I mean, yeah, before knowing that it's actually in my book, I actually wrote down a very detailed proof. But I think at least the way I do it, it's very difficult to know what it is. You can just write, you have a lot of enough generators to generate the rings, but what the equations is difficult to know. No. I mean, there is this, but there's also the fact that the omega x, it's a section of omega. I mean, this is what it's not even know when you have enough of one form on the surface. It's not just that, but it's somehow connected, right? Yeah. It's yeah. No, so no lecture. I don't think. Yeah, I mean, it's a connection with the fundamental lemma somehow, but that's it. There's no connection. Sorry about that. Yeah.